this recording we will talk about relationships between objects and classes. My name is Tobias Olsson and this work is licensed under the Creative Commons Attribution Share Alike. During this recording there will be some examples, and these examples are related to the exercises presented in previous recordings. So if you don't want to know the so to speak correct answers for these exercises before you have done them, I suggest that you try to do the exercises first. So we have previously seen a couple of types of relations between objects in our examples. And we use these relations to send messages between the objects so that they can collaborate and do things. This technically means that we call methods on objects. And to be able to call a method, we need to have a relationship between the objects. In the example, we saw that the dice game class had two attributes of type dice. And this means that the object created will have a connection to two dice objects. We call this connection an association. In UML, we show this in the class diagram by using this type of arrow, an open arrowhead and a full line. There are, of course, other ways also to form a link between objects. We can send an argument to an operation in the object and supply an object in that way to the method. We saw this also in the dice game because the player class had an operation have fun, and in this operation we sent the dice game object. There were no attribute in the player class of type dice game. This means that we have a relationship called a dependency, and in the UML we show the dependency by using a dashed line and an open arrowhead. So this is an important distinction to make between the association and the dependency. Instead of sending an argument, we can of course also create a local variable of inside a method, and then it also becomes a dependency relation. And we can call constructors, static operations, etc. This also creates a dependency. In general, dependency is often the word used to denote a relationship between two parts in a software system. I try to use the word relation so to separate dependency from the other types of relations we can have. But if you hear the word dependency, often it's meant to denote some type of relation between two objects, or one object needs the other object in some way, or one module in the system needs some other module in the system in some way. And you can have that in mind when discussing with people, that it's often not this very tight distinction that we make in this course between the association and the dependency. Actually, also in the UML, the dependency is defined as the most general form of relationship that we can have. So if you don't know what type of relation you would like to have between parts of the system, you can always opt to use the dependency as long as you don't know or don't want to decide on anything more special. The main question now becomes when should you use dependency and when should you use association when designing? It's important to realize that you make these decisions even if you don't do a visual diagram. You do the design by coding. So even if you don't diagram on paper or in a tool, you make these decisions when you implement. So sometimes we forget about that. So you do design even if you don't draw diagrams. There are a few reasons to using an association instead of using a dependency. So maybe you have some kind of benefit for keeping a relationship between calls. Maybe several methods needs to use the same object, and maybe it's hard to create this object, and it takes a lot of code to just create the object. Then it would be beneficial to create it in one place and then use it as an attribute and not create it as a local variable, for example. This ties into the concept of class cohesion, and it basically states that most of the operations methods in a class should use all of the attributes in the class. So if you have a lot of methods that use just one of the attributes and a bunch of other methods that use some other attribute, this is an indication that maybe this class should be split into two different classes, because one part of the class seems to handle one type of responsibility and another part of the code in the class seems to handle some other part. So if you can find attributes that all of the operations need, it's a candidate to use these types of attributes as an association. More importantly, you may need to remember the relationship between the objects during the program execution. So we need to preserve the state of the program in some way, and we can do this by using association. So between method calls, you need to have used the same object, because at some later point in time, the state will be manipulated. And this time can be as short as the next method call, so to speak. And maybe we also have some kind of persistence. We need to load and save things between executions, and this can be then it can be beneficial to use the association. Also, maybe it makes sense from the requirements point of view. So you have some requirement, you have some understanding of the domain, and this indicates that, okay, this should be contained in this object. So this object should contain other objects, because that's what that's how the domain works. So it would make sense to understand the code base based on the domain knowledge that you maybe have. So if one or more of these criteria fit, then you should consider using association. So does it make sense? Do you need to remember the relationship between objects during execution? Do you have a benefit from keeping the relationship between calls for some reason? And think about the class cohesion. The default is that you should opt to use the dependency. So basically, passing arguments is often the best choice and creates the most adaptive design. It becomes often easier to test if you use arguments to method calls instead of using associations. But sometimes associations are needed. Going back to our little example here, we saw that we had this association from dice game to dice, but they are technically not needed, as we could just create the object as local variables inside play instead. And we see an example of this here. So instead of having the attributes for the dice, we just create them as local variables, and then we use them, and then they are destroyed automatically when the method returns. So the reason for using them as attributes in this case is that, well, it makes sense from the domain point of view. The dice game contains the dice in reality, and this hints us at using association for the dice. And I'm also thinking a little bit of the future here. So what if we want to know the value of the dice we rolled at a later stage? These values are lost in this if we use them as local variables here. We don't know the sum really. We just know if we won or not. And maybe this is something that we would like to know. This means that the dice game needs to keep its state. It needs to know about the dices between calls, so that we can add another method to get the dice values. So we can imagine that the player is not happy. It does not just want to know if he won or lost. He also wants to know what the actual values of the dice were. So if we have the association, we have the objects created in the constructor, we use the object and they keep their state between calls. So we can add another method called, for example, get dice values, that return an integer array with the two dice values in it. And then the player can first call play and get the result, there is a win or not, and we can then get the dice values so we can print them also for the player enjoyment. So basically this is the motivation for using the association in this case. It makes sense from the domain perspective, and we need to keep the state between two different calls. So in play, the dice are rolled, their state is set, their value is set, and then we get these values at a later point in time. So we can have relationships between objects, association or dependency, but we can also have relationship between classes. In the first recording, we talked a little bit about one of the benefits of object orientation, that it could express general hierarchies with specializations in it. And this we can do with the class relation called generalization specialization. And you may know this as inheritance, as it's commonly used in programming languages. In UML terms, it's called generalization specialization relationship, and we use this type of arrow here to indicate that. So it's a filled line with a closed arrowhead. So it's important to not mix this with the association relationship when diagramming, so you don't think that you're using inheritance instead of association. The main benefit of inheritance or generalization specialization is that we can reuse code. So we can have common behavior in more general classes, and we can have special behavior in more special classes. So this means that we can put common operations or attributes in a more general class, and we often call this class a base, parent, or superclass. And then we use the inheritance to have special classes, subclasses, or child classes to reuse these common things. And in Java, we use the keyword extends when we define the class. And we can also override operations to provide special behavior. So if the parent class has one generic type of behavior, we can override this in the child class and make the behavior as specific as we want it. In some cases, we also conceptually want to capture a relationship that we can see is kind of like inheritance. We have this X is a type of a Y thing. So if we find that in our requirements or in the domain, we have an indication that, well, maybe inheritance could be a good thing here. There is a little bit of a warning here that it's often quite hard to transfer these into a concrete design. So if we find something that conceptually seems to be inheritance, it's sometimes hard to transfer it to the details of the code, because there are so many details to think about when implementing and coding, and it can be really hard. And we also have this tendency as humans to make things a little bit simpler than they actually are, and natural language reflects that. And it's sometimes we think that inheritance could be a good thing, but it really isn't. My take on this is that if you find code duplications, you have duplicated code in your code base, or you're simply copy pasting between a lot of different places, then you should consider using inheritance. And you should then use inheritance if the classes are conceptually related. So you can say that X is a type of Y, and it makes sense. And also that 100% of the base class applies to the subclass. So everything in the base class should be applicable to the subclass. You should not have the case where you have maybe an attribute in the base class, and this attribute is never really used in the subclass in any way. It's kind of like a dead part of the base class that you don't use, just to reuse some method or something like that. This ties into one of the principles that are in the book, also called the Liskov substitution principle. And we will actually take an example here so that you can see that natural language is not always the the best way to find these types of hierarchies. In this example, we are simply taking the conceptually correct idea of a square being a special type of rectangle, and we can see this in this little class diagram here, that the rectangle is a more generic concept. It's more general, and we have this more special concept, square. So the rectangle has a width and a height. The square also has a width and height, but it just makes sure that the width and the height are always the same. So in the rectangle we have the attributes width and height, and we have operations like set width, set height, and calculate the area. And then we reuse the code in the rectangle class, and we provide special behavior for set width and set height. So when we do that, we make sure that we set both the width and the height so that the square is always a square. And then we calculate, have the same type of behavior for calculating the area, width times height, simply. To test this rectangle class, we have written a small test program here that says that, okay, we create the rectangle object, we call this test rectangle area, where we send in the rectangle object, and we send in the width and the height. And in the test rectangle method here, we set the width and we set the height on the supplied rectangle, and we do a little printing so that we can compare the calculated area from the rectangle with the expected area, the width times the height, so that we know that the person implementing this has done a good job. So the exercise is to implement the rectangle and the square classes, use inheritance to reuse the code in the rectangle and override set width and set height for the square, and then run the test program and see what happens. Let's continue with the dice game, and we will take a look at how we can use inheritance to provide a nicer code base without a lot of duplication in it. And the idea is that we want to provide a variation of the game. So the player gets a reroll of the first dice if you have not already won. So if you don't get the 7, you get to reroll the first dice. And we will make this a little bit simpler because the player does not choose to reroll it. This will happen just automatically. So it becomes a little bit easier to win here. We still want to keep the original game. So we should be able to play both variants in the same execution. So maybe first I want to play the little bit harder game, and then I want to play the little bit easier game. So if we design this by not using inheritance, we get code duplication. We implement a new dice game variant here. It looks very much like the original dice game. You have 2 dices. We create the dices in the constructor. We call play. We roll the dice. We collect the sum, and if the sum is not 7, then we re-roll, and finally we return the win or not. And we have the get dice value. So basically it's just this little part here that is actually special for the dice game variant. Everything else is just copy pasted from the original dice game class. Also in the player we have this new have fun operation that instead of the original dice game takes the new dice game variant, and it does exactly the same thing as the original have fun method. But in this way we can play both dice game variants, and the design looks something like this. So we have the player, it depends on the dice game, and it also depends on the dice game variant. The dice game variant also has 2 attributes, so it has 2 associations to the dice, and the dice game also has its original 2 associations to the dice. And maybe already here we can see visually that, well, okay, dice game variant and dice game, they seem to be conceptually related. You can take a look at the names, and well, they seem to be be related like that, and they also have the same attributes here. So we have the same relations to the dice. So this indicates that inheritance could be a good thing. And looking at the code, we can see that we have duplication in the player. It does exactly the same thing with the two types of dice game that we have here. And also in the dice game variant, it very much looks like 75% of the code is just copied from dice game. So instead of doing this type of design, we use inheritance. And we simply let the dice game variant be a more special type of dice game. And the class diagram looks something like this. So you have the player, it depends on dice game. Dice game has two associations to dice as usual. And the dice game variant is a special type of dice game. It inherits from the dice game. In the play operation, we need to do something special in the dice game variant. And basically we need to have this statement that if we don't have one, we need to reroll. So the behavior first is to do exactly as the parent class does implement play. So we start by calling this. And this we can do in Java by using the super keyword. So we use the implementation of this super class inside of the more special class here. So that's the first thing we do. And if we don't win, we call roll on the first dice, and we recalculate the sum, and we recalculate the winning condition, and then we return. And we need to do one change inside of dice game. We need to set the dices to protected so that subclasses can access them. And this way you can let other classes than the original class access stuff in a parent class. So every child class to dice game can now access the dice objects inside them. And we actually don't need to make any changes to the player class because the player is only dependent on dice game. It does not really know that there is a special type of dice game also. And this is because most object-oriented programming languages implement something called polymorphism. And this is the ability to bind to an implementation at runtime. So when we compile the program, the player class does not really know about this special type of dice game. But when we run the program, the method called play should go into the subclass of dice game and not end up in the parent class. So when we run things, we need to bind to the correct method. And this is what polymorphism offers. So the exact concrete type of class of an object is not known when we compile. Both the dice game object and the dice game variant object support the play message, but we have different implementations. This is also something that we call late binding. Using polymorphism increases abstraction, and we can decouple the classes more. And this is an important thing because and this is something that is discussed in previous recording, that because looking at the types of relationship between the classes, we can make certain decisions easier. So we want some things to be connected and we want some other things to not be connected to each other. And by using polymorphism and inheritance, we can increase the abstraction and decouple. And we saw this also in the two variants of the class diagram. Looking at the player class, it's connected, it's dependent on dice game in this design. It does not know anything else. In the previous design, the player class is dependent on both the dice game and the dice game variant. It knows about both of these classes. Reusing the player class indicates that we need to reuse both the dice game and the dice game variant. In this design using inheritance, we only need to reuse the dice game. We don't need to reuse the dice game variant. So we have decoupled the player class from the dice game variant, and this has also reduced code duplication. And this means that client classes, for example, the player is not bound to concrete implementation. It's not bound to the implementation of play, but the actual implementation can vary depending on the type of object actually used when we run the program. And it's the signature of the operation that is what matters at compile time. So we call play on different types of game objects, whether it's the original dice game or it's this new dice game variant. And one thing to think about is that if we change the signature in the parent class for some reason, maybe we just rename the method, then we can have some really strange effect, because then the polymorphism will not work, because the original method in the subclass will just be another method and it will not override the thing in the parent class. This has been fixed a little bit in Java by supplying the override annotation. So you can say that, okay, this method should be something that overrides something in a parent class, and you will get a compiler error if you change the signature in the parent class and you forget to change it in the subclass. Another interesting idea connected to this is the concept of abstract classes. And this means that we can still provide reusable code in a class, but some operations are mandatory to implement. So we don't supply an implementation for these in the abstract class. So you must override them in subclasses. This fixes some of the problems of changing the declaration of the method, changing the signature of the operation, because as it's mandatory to override it, you will get the compiler warning anyway. Abstract classes are special because you cannot have objects created from this type, because it's an abstract class. There is missing behavior in them technically. Also, this ties into the ability for us humans to make these abstractions. And for example, you cannot really go into a store and buy a fruit. You buy something special. So you buy the banana or the apple or the pear, but you cannot really buy just the fruit. A fruit is just an abstract concept. So if you go into a store and ask to buy a fruit, the personnel will get really frustrated when you don't decide what the actual fruit is that you want. So this is something that abstract things exist in our reasoning as humans also. So basically you declare the class as abstract, and you declare some of the operations as abstract also, and there is no implementation for these in the abstract class. So the subclasses must implement these or the compiler will complain. And compiler complaining is a good thing, because then you know what to do. There is a huge benefit to have the compiler catch errors as soon as possible, and basically this is one of the great benefits of using a compiler and having a type-safe language, because we know that we have done some of the basic things right. We don't need to execute the program to find these types of mistakes that's so easy to make. So if you get compiler errors, it's a good thing. You know what you have to do, you read the error message and you understand it and you make the fixes. So the abstract classes also combats this problem of changing the signature of base class operations. The final type of relation between classes we have is the realization relationship. And this is abstract classes taken to the extreme. So we have some class that is completely abstract. It does not provide any type of implementation in its code. It's the implementation is completely in the subclasses. And this further facilitates decoupling and abstraction. So the client classes only see this interface, this this bunch of operations that encapsulates the simplest way to use these subclasses. So we try to create a list of operations that present no implementation, but just the signature of the operations. And we try to make this set of operations as simple as possible. This is not that easy to achieve because they cannot be too simple, or the client classes cannot perform the desired behavior at the desired level of detail. So it is not uncommon for these interfaces to be unstable to start with, because you don't really know exactly how these interfaces should be used and what level of detail you need in the interfaces. Another benefit of using realization is that we can have dependency inversion. This is also one of the principles discussed in the book. And basically long chains of classes are hard to reuse and maintain. So if you have these long chains of relationship between classes, you can imagine that if we want to reuse some of the first classes, we have this long chain that we also need to reuse. And basically we need to understand the whole chain of stuff to be able to reason about it well. And this becomes hard when the chains become longer and longer. We also can have the problem of circular relationships between classes, and these are basically relationships that in some way go around in a circle, and these are known to be hard to reuse and maintain because you need to take everything in the circle as one unit, so to speak. So this is something that we want to avoid, the long chains, and we want to avoid circular relationships because it becomes hard to reuse and maintain. Also, another thing is that most object-oriented languages do not support multiple inheritance. So we cannot inherit from several base classes because this is complicated from a technical point of view to solve, and behavior can be somewhat strange. So in some cases we want to be able to have the idea of multiple inheritance, and then we can use the realization instead. And in UML we have this type of notation for the realization relation. So it's a dashed line with a closed arrowhead. And this should of course then not be confused with the dependency relationship. So inheritance or generalization specialization needs to be separated from association. Realization needs to be separated from dependency. And to use the realization relation between classes, you need to define and create the interface first. So in Java you use the keyword interface, and in the interface you define the operations and you don't supply any implementation to these operations. And you can also not have any associations because you cannot have any data in interfaces. They are completely abstract, so to speak. And then we use the realization relation. In Java this is called extends, to specify that the class should implement the operation. So it's mandatory for this class to implement the interface, or the compiler will complain. Again, this is a good thing. Now there are some special things in newer versions of Java with default implementations for the interfaces, but I suggest that you don't use that. So an example, we want to reuse the magnificent player class in another project. As we saw from the previous design, the player class is connected to the dice game, and the dice game in turn is connected to the dice. And we simply don't want that. We want to just reuse the player class as easy as possible. So we don't want to reuse dice game, and we don't want to reuse the dice game variant. We also want to introduce another type of fun game, but it's not a dice game. So using inheritance from the dice game does not make sense. We cannot say that this game is a type of dice game, and we don't need the dice for this game. Instead, this is an amazing time game. And we use the time of the computer and see if it's evenly divisible by 7, then the player wins. And as I said, this dice game has nothing to do with dices at all, but you can play it and you can get the result from it. So instead of using inheritance, we define an interface, and we call this interface game because it's the most generic thing a player can do. A player can have fun with a game. And you can see the design here. The interface defines the method play and defines the method get result. And the player is now dependent on this interface. We have two realizations, time game and dice game. Both realize this interface. And we also have the dice game variant that inherits from the dice game. The dice game, of course, still has the associations to the dice. In this way, player is completely decoupled from the exact implementations of the games, and we can have radically different implementations. So we can have games based on dices, and in this other case we have game based on time. The player can use these different implementations just by using the operations in the interface. And the interface is also super easy to reuse because it does not contain anything else than the operation definitions. So this does not have any dependencies to anything, which is good because before that we needed to reuse the dice game and then we needed to reuse the dice. So we have reduced the complexity of reusing here, and we have provided a way to have games that are not bound to using a dice. So the interface simply looks like this. You define it as an interface, you give it a name, game in this case, and you provide the operations that should be in the interface. And we provide the keyword implements in dice game so that the dice game implements the interface. This is what actually creates the realization relationship in the UML class diagram. And we override get results and also the other operations, play of course. And in the time game should also implement the game interface. It has a result, and it has the play operation, and it has the get results operation. You call play, and the exact implementation depends on what type of object G actually is. So if it's this new time game, the implementation in time game will run. If it's a type of dice game, then the dice game implementation will run. If it's a type of dice game variant, the implementation in dice game variant will run. But for the player, all of these objects look the same, so it does not really care that it's a special type of game that is played. It only cares that I can call play, I will get a Boolean value back. I can call get results and I will get an integer array back. So this is the concept of having an interface, of using realization. And we use the polymorphism and late binding of the programming language used to, when we run the program, then it's decided what code is actually executed. Finally, we have something that I usually nag a lot about, and these are what I call hidden dependency. And a hidden dependency is something that is not explicitly a dependency in the source code or in the design. This means that such dependencies are not checkable by the compiler, and this is bad. Basically, it indicates that you will need to change something in several places in the code base for things to work. And the developer must know about these places, because if the developer does a change in only one place, you will have some kind of a bad behavior of the system when it runs. So as a developer, I must remember, oh, if I change this in this place, I must remember to change it in several other places. Basically, we have the compiler as a helper. So if you change, for example, a method name, the compiler will tell you that this method name has changed, and the system will not compile anymore because you have forgotten to change this in other places. But these hidden dependencies are bad in the way that the compiler does not know about them. So you as a developer must manually remember this. One example is that you have hard-coded constants that must match in several different places of your code base. So maybe you have a menu or something in your console that says press 1 to do this. In another place in the code base you have a hard-coded integer or a character or a string that contains the 1, and this 1 must match the thing that you printed in the menu. So if you change the menu to something else, press Q to do this instead. Then you must remember to change this in some other places also, or the menu will not work as intended. Typical example of hidden dependency. So if you have hard-coded constants, because they are so convenient to use, you probably have a hidden dependency. Typically you have integers that must match, strings that must match, characters that must match. Maybe you have order of operation calls that must be in some special way. So first you must have call this operation, and then you must call this other operation. Also examples of hidden dependencies. Maybe you put things in a certain order in an array. So first you have an array of strings, and first you have the first name, and the second string is the last name. And in some other place you use this order, and if the order should change, then you need to change this in several places in your code base. Typically hidden dependencies, and this is not something that you want. So the solution is to try to make them explicit. So instead of hard-coded constants, use enumerations or constant variables to replace them. You can create some common operation maybe in some class that can be used instead of using these hard-coded constants, or have the order of the operations encapsulated in this operation instead of remembering to do this in a certain order all the time. Unit tests can help in alerting developers of needed changes. So if you have automatic unit tests, you sometimes can catch these hidden problems that can crop up when you have hidden dependencies. So the system does not behave as it should anymore, and you may catch this in unit tests. And you can of course document this hidden dependency as a dependency in the class diagram and make it explicit, so that you can at least see that, okay, this is dependent on this in this kind of way, even if it's not an argument, a constructor call or a local variable or something like that. It is a dependency, and we need to remember that this dependency actually exists, and the compiler does not help us. So try to avoid hidden dependencies. In the example, we actually have a hidden dependency between the dice game variant and the dice game. If you remember, we hard coded this winning number here. So this is hard coded in both places. And if we decide, no, we should not have 7 anymore, we should have something else, and we change it in dice game, we must remember to also change it in the dice game variant. And this is another type, another file. So it's not easy to just see that, okay, the 7 is here also, and typical hidden dependency. And also looking at this, we have some code duplication here, because these two statements are actually exactly these two statements, and this statement is basically this statement also. So this is something that we should look out for. But the real badness here is this hidden dependency between the dice game variant and the dice game. And instead of having this hard-coded in both places, we create a new operation that we can use in both classes, instead of having the code duplicated and this hard-coded constant in several different places. So basically we call it isWin, and isWin simply gets the value from the two dices and checks if they are 7 and then returns true. So we then simplify the code in play also significantly, and we simplified the code in dice game variant also. So removing these hidden dependencies and code duplication has a real impact on the maintainability of the code base, because it becomes simpler, it becomes easier to understand, easier to reuse, and less prone to problems and bugs. So let's do an exercise. The exercise is to create new versions of the linked lists, the single linked list and the double linked list. And we should store something else than this boring string. We could store, for example, an exciting integer instead. So you should try to use inheritance to remove some code duplication, and possibly use an abstract base class. And a challenge is to do this without using any casting, or at least as little casting as possible. So you don't want to use casting if you can avoid it. This relationships is an important topic, so let's try to do a summary. The first thing is try to manage with the dependency relationship. Sending arguments is more flexible than using association. So if you can get by with using dependency, it is often the best option. So you should use association if it makes sense and if it is needed. So if you use the same objects in several operations, you can opt for association, but you should also think about this class cohesion stuff. If you want to keep the object states and use the same object between calls, then it makes sense also to use association. And also if it makes sense to store the system state in some way, and in many cases we need to have some living state, so to speak, in our application, because that is what we are operating on all the time. That is what messages are sent to all the time. So we need to keep this state for the system in some way. And it should also make sense from the domain point of view, of course. The dice game contains the dice, so it makes sense from that point of view. We use inheritance, or as it's called, generalization specialization, to reuse common code. So if you are copying code between classes, or if you are copying whole classes, it could make sense to reuse this code via using inheritance instead. But make sure it also makes sense from the is a perspective and the 100% rule. You can use realization to invert dependencies and decouple classes even further. So watch out for circular dependencies and make sure you find strategic points of change. And this is not easy. For example, in the dice game, the point of change is the type of game that you want, and it can be radically different types of games. Then we create an interface and try to get the right level of abstraction there also. Not too much detail, but also not too simple. We want to avoid hidden dependencies, watch out for hard-coded constants, and visual models can help. For example, typically the class diagram is where you see these relationships visually. And you can sometimes even see that, okay, you should probably try to reuse this in some part. And we have circular dependencies, for example, and then we should try to avoid that by using an interface in some way. And these are design decisions that you make. You decide how the objects are to connect to each other, how the classes are to connect to each other. And even if you don't use visual modeling, you make these decisions even if you make them in code. So every time you introduce a new relationship, you do something to the design of the system. And visual models can help you see what you actually have done. I hope you learned some more interesting things about object-oriented design and the relationship between objects and classes.